In addition to t-tests, we can also construct confidence intervals for linear contrasts. So a confidence interval for a linear contrast is very similar to a confidence interval for any random variable that follows a normal distribution with an unknown variance. So we would construct a confidence interval for a linear contrast like this. A 100 times 1 minus alpha percent confidence interval for our parameter of interest, which is this gamma, which again is just the sum of c sub I times mu sub I from I equals 1 to a, is written like this. So we have our point estimate for what gamma is, that's our c, and remember the big C is just each contrast coefficient times the sample mean. So we're plugging in the sample mean for mu sub I. We're plugging in y sub I dot bar. We add those up from I equals 1 to a, plus or minus, and then we have our t critical value. So that would be t alpha over 2 with n, big N, minus a degrees of freedom. Again, that's the total number of samples, and a is the number of levels. And then we multiply this by the standard error of this point estimate here, which occurs in the denominator of our t statistic, and it's the mean squared error divided by n times the sum of all of our contrasts squared from I equals 1 to a. Sorry, contrast coefficients squared from I equals 1 to a. An important fact to note is that while the conclusions of the t-test for linear contrast aren't sensitive to the scaling of the contrast coefficients, the bounds of our confidence interval are sensitive to the scaling of the contrast coefficients. So let's construct a 95% interval for our coffee example. So again, our point estimate here for our contrast, that was negative 4.153 plus or minus our t critical value here. So this t critical value that we're looking for is, we're looking for the value, let's write it out here, a t random variable with 10 degrees of freedom that is greater than this t, let's see, the alpha level would be 0.05, so if it's a 95% confidence interval, so our alpha over 2 would be 0.025, and our degrees of freedom are 10. So we want to find this quantity here is going to be the quantity such that the probability a t random variable with 10 degrees of freedom is greater than this quantity is 0.025, what we see right here. So if we use R, we can find what this value is, or we could look it up in a table, but it comes out to 2.228. Okay. So we do plus or minus 2.228, and then we multiply this by the standard error of our estimate for the contrast, which again is what we saw in the denominator, which is the square root of the mean squared error, that's 9.842, divided by our sample size, which is 3, and then multiplied by the sum of all the contrast squared. So, or the square of the contrast and then sum them. So that, again, comes out to 1. So our confidence interval goes from centered at negative 4.153, plus or minus, working out this math, we get 4.036. And again, we'll see that this confidence interval doesn't overlap with 0, and so that's consistent with our conclusion from the t-test. Now, if, for example, we were to, instead of using contrast coefficients of 1/2, let's say we had multiplied all of them by 2, we would have gotten the same exact conclusion that we got for the t-test with the same p-value and everything. But the difference would be that our confidence interval, while it still wouldn't overlap 0 and would be consistent in that way, our confidence interval would now be centered at negative 8.3 about, so twice this, and it would be plus or minus about twice this here, 8.072 or so. So what you put in for your contrast coefficients does matter, and so you should try to pick things that make sense. One way to get around this is to use standardized contrast coefficients, which are basically the standardized contrast coefficients look like this. We denote them with a little star, so C sub I star is equal to C sub I divided by the square root of 1 over n times the sum of all of our contrasts squared. Sorry, the sum of each contrast squared summed up. From I equals 1 to a. So what this does is it makes it so that the variance of our estimate for the contrast here is equal to sigma squared, and so it's in that way it's standardized.